we can get started. You're the man can dim the lights a little bit. So unless you were hiding under a complete rock, sometime this summer you probably saw a Nature paper from ESO with some beautiful VLT news imaging of the supernova remnant with a big double detonation shell and some calcium, and this completely took, made my jaw drop. It was a beautiful image. But what's particularly rare is that double detonations are like less than 1% of all type 1A supernovae. And for a brief while, 50% of all of the double detonation sample that was out there was thanks to one person, our local speaker today, Estefania Gonzalez, who is now at Johns Hopkins University / Space Telescope Science Institute as part of the Transit. Estee did her undergraduate work at Cal State Bernardino, where she mentioned this morning that she was actually living at home with her mom and dad so that she wouldn't go into debt while doing this, which is incredibly hardworking. And at the time, she was not studying very large things. She was studying scanning tunneling microscope of very small things. But she went on from Cal State Bernardino to UC Santa Barbara, where she worked with Andy Howell and was part of the team that found the first two really convincing examples of double detonation supernovae. It's likely that Rubin will find more of these things in the next few years. So I figured it was a good time, since this seems like an interesting progenitor channel that we should think about for these particular modes of stellar death, to have quite literally the expert in the world who knows more of these objects than anyone else. Estelle, take it away.
Thank you so much. I'm really excited. This is my first colloquium, and I'm really excited to talk to you about different ways on how we can explode a white dwarf, and also a little bit more of the global properties on how the brightness of the supernova can change depending on the host environment. Okay, so this is what I'll be discussing today. An overview of type 1A supernovae. For slide 2 and 3, those are double detonation candidates. So it would be with variations of the helium shell, and I'll explain a little bit about these models. And also I'm going to talk about what could be causing the variations of the supernova brightness, and how does the environment play a role. Okay, so a little bit of motivation for type 1A supernova is they're using cosmology. So it was realized in the 70s and the 80s that even though supernovas brightness can vary, and also the light curve can have different shapes, you can actually standardize them. And that is because we know the luminosity and decline ratio, or the Phillips relation. You can use this to standardize them. And actually, it has been really important as cosmology tools, because if you can standardize them, you can measure distances between galaxies, or just distances in general. So here on the right, so you have here the variations of the luminosities for different type 1A supernova. What's also interesting is that because of them, in the year 2011, they use this to discover that the universe is actually accelerating. And so not only they use supernova, but they also use different methods. So you have like really precise measurements, and also you have the different temperature fluctuations coming into play, but you also have different like density distributions of galaxies to come into play to show that the dark energy is about 0.7. And what's also really cool about the supernova 1A is that you had different groups working on this simultaneously. They had different data. They also had different tools, and they both came to the conclusion that that the universe was accelerating, and a Nobel Prize was awarded. So I discussed how supernova 1A can be standardizable. And here on the black, you can see, or this line right here, those are the normal supernova, the ones that are standardizable. However, there are different subclasses of supernova that are not standardizable, and they're intrinsically different. Some of them are intrinsically less luminous, so you have the 91 BG lights. Some of them are brighter than 91T likes. And so this just goes to show that even though we have an idea what the explosion mechanisms of the supernova are, there's so many variations that we still to this day don't really understand exactly how we explode these. So let's take a step back to try to understand where supernova came from. So supernova, or in general, stars come from stellar clouds, primarily composed of gas and dust. But for type 1a supernova, we're gonna focus on the small star. These have masses that range between 1 and 8 solar masses. After you have the hydrogen fusion into helium, and when it runs out of hydrogen, the core gets really compact and hot, and it causes some of the layers to expand outwards, or a red giant. These layers get so far away that at some point they're not bound to the star, and they get ejected into space, leaving a white dwarf behind. So the question is, how do you explode a white dwarf? Can a white dwarf explode? Well, the answer is no, but not on its own. You need something to cause these to explode. So here are two different channels of the explosion mechanisms of these white dwarfs. So the main scenario, or the classical view that most people have, is the Chandrasekhar mass explosion model, where you have a carbon and oxygen white dwarf, and you have it's in a binary system with the main sequence star, and they collect some of the hydrogen, and because it's a degenerate core, at some point, when you approach the Chandrasekhar mass limit, it causes a thermonuclear runaway. And the way that this explodes is still like not very well understood. But the main way that you can explode this is via a delayed detonation, and I'll discuss this a little bit more in detail. But there are different ways to explode this. You have the pure detonation, pure deflagration, and a combination of both, delayed detonation. Now, the other way to explode a white dwarf is instead of having what about having a smaller carbon and oxygen white dwarf, having a sub-Chandrasekhar explosion? So you need a smaller white dwarf, and that would be in a binary system with the helium star. So you're creating some of the helium, and what happens is that this helium begins to actually get really hot as you're like piling the helium. It gets really hot and it begins to explode. So you have a detonation here on the surface of the helium shell.
There's a big stick in the corner if you want to point it.
Oh.
Just behind you. Yeah. Okay.
Oh, great. So what you end up having is a detonation here in the helium shell, and that causes and compresses the white dwarf. It sends a shockwave to the core, and the secondary detonation happens. So these are why they're called double detonations, because you have two explosions. And I'll talk a little bit more about what those are, but those are the main scenarios. So now we as a community agree on some of the basic properties of these supernovae, of what a supernova is. So you have the volumetric luminosity, or the magnitude. So it's about -19.2 normally at type 1a. The rise and fall of a type 1a is about from time of the explosion is about 19 days until maximum light. So for the spectrum feature, some of the elements that are key are the silicon. So here, and that is because of all the intermediate mass elements that it creates. And the light curves are powered by nickel. Okay, so going back to the models, so I showed two models, a classical view that was on the left, and so here we're going to discuss this a little bit further. I mentioned that the delayed detonation is probably the way that they explode, and the reason why it's believed this is because if you have a pure deflagration, it's a subsonic explosion. It puffs things up. But it doesn't cause a complete burning. So you have a lot of intermediate mass elements, and the problem with this is that you don't get enough nickel. So what ends up happening is that a lot of these supernovas that are from the model of pure deflagration, they're not bright enough to be a normal type 1a. Now, if you had a pure detonation, on the other hand, a supersonic explosion, most of the material gets converted to nickel, so you have really bright explosions, which also does not match a type 1a. However, if you have a combination of the two, where you deflagrate, you puff things up, and then you insert a detonation, maybe you can get something that looks like a 1a. So here is the example of a delayed detonation, where you start with the hot spot, you puff things up, it comes around the shell, the deflagration, and then you insert artificially a detonation. And for the most part, this is the way that it's believed. And they seem to match observations, not perfectly, but they seem to match much better than the other two approaches. Now, what are the problems with this model? Well, to begin with, the accumulation of hydrogen is very difficult. So you need a way to retain some of the hydrogen. So if you have too much hydrogen dumped, you have a radius expansion, and so a lot of the hydrogen gets ejected. Now, if your m dot is too small, you end up with a classical novae, where you also eject a lot of the hydrogen. So that's really difficult to retain the hydrogen, to cause the explosion to begin with. Now, as I mentioned, they're also in a binary system, and so you, for models, you should be able to see the shock interaction with the binary. So this is what the light curve should look like if you have no companion, and then with different masses of the companion, and especially for a red giant, you would be able to see this bump. It could be the case that maybe the companion is a small main sequence star, and so it would be somewhere here. But for the most part, the light curves they don't really show this bump, which is interesting. But we can't fully rule out this scenario. Moreover, no hydrogen has really been detected in this spectrum. And we haven't really seen compelling evidence of surviving companions, really. I mean, if this is a primary scenario, we should be able to see more of this. And furthermore, that delayed detonations are still not well understood. So on the previous slide, I showed you of the way that this happens, but we don't understand the transition between the deflagration and the detonation. We just simply assume that it happens, and we just inject some energy and say, okay, this is how it happens, but we don't really understand why that is. Okay, so now the other scenario, the question is, how can we explode a sub-Chandrasekhar mass white dwarf? So you have a smaller white dwarf to begin with, and in a binary system, it dumps some of the helium mass to the carbon and oxygen white dwarf. So I'm gonna show if it works. Should be a little moving. Oh, no.
It was working.
It was working?
Yeah.
Oh,
Yeah, just hit the play button again.
so this is a video showing how the double detonation explodes. So the helium begins to detonate. And so these are simulations from SAMVUS. And that is when the secondary detonation happens at the core. Now, the models can look very different depending on how much helium you accrete. On the white dwarf, so for example, you have two different scenarios where you have 0.1 solar mass of the helium shell and 0.02 solar mass. The main difference that you see is that when you have enough helium on the shell that gets secreted, you create a lot more of like these intermediate and iron group elements on the outer shell. So you end up with a lot more material, and that is because of the helium begins to burn and it creates a lot of these intermediate iron group elements. And why that is important, I will explain. So because of this, that as you may imagine, the observations can affect the observations. And so what do these observations look like? So here are two examples of these double detonations with different masses of the helium shell. So here on the left is with a tenth of a solar mass of helium, and then here is 0.08 solar masses of the helium shell. And as you can see, when you have small helium shell, the light bursts look a lot smoother than when you have more helium. And that is because of the because you have more of this like chromium and like intermediate mass elements when they decay, especially with chromium, you basically they'll pack light. You'd expect to see some of this bumpiness. But overall, if you have a thinning of helium shell, they seem to appear to match the light bursts of a type 1a. Okay, what about the spectrum? Well, the story holds true for the spectrum as well. For the spectrum, here you have the thin helium shell, and then you have the thick helium shell scenario. So these are in log space, so they look a little bit different. But you often do see the silicon feature, and then the titanium features can change depending on the thickness of the helium shell. And so it, for the most part, matches really well with the spectrum for the type 1a supernovae. However, on the other hand, if you have enough helium shell, you end up with some blanketing, especially the more, especially for these ones at maximum light, you end up with a lot of blanketing. So these are the masses of the white dwarf. And with this ones, you'd expect with more masses of helium to blanket a lot of these U light, and that is because when you create all of these intermediate mass elements, it absorbs a lot of the blue light. So by comparing the supernova light curves to theory, there has been studies that have found that the total mass of the ejecta of supernovae, about 50% of them were less than the Chandrasekhar mass limit, implying that a lot of them could come from sub-Chandrasekhar mass white dwarfs. And so again, these double detonations have not widely been accepted because the observations to the models are a lot redder. The models are a lot redder. And so it was not widely accepted for a long time. But I'll go ahead and give examples of the different things that we found. But then the question is, if that's true, if about 50% of them are expected to be sub-Chandrasekhar mass white dwarfs, where are they and where can we find them? Okay, so now I'll talk about our first scenario. So this is supernova 2019 EIX. It was originally classified as a type 1c because of its brightness. It was minus 19.2 for net normal type 1As. They're normally minus 19 magnitudes. I'll start here, but if you look at the Phillips relationship, these are the normal type 1As. This is where 2019 EIX was located in relation to the Phillips relationship, which was nowhere near the Phillips relationship, very different. It actually matched more like the one in terms of like the brightness and the luminosity relation. And this is what the spectra look like, which as you can see, there's a lot of like blanketing. It's a lot brighter than what you expect for a normal type 1. And it's also a lot different than what you'd expect for a type 1c. So this is the spectrum evolution of a type 1c. So the very first spectrum that we had, so these are all of these phases are with respect to the maximum light. So you have minus 4 days from peak. So this was the first spectrum that we had, and it did appear to look more like a 1C. The one thing that caught my attention was that the oxygen feature was absent. And the oxygen feature is actually one of the key features for 1C spectrum. And as it evolved, it also looked very rare. So I compared, I compared the evolution of these supernova with different supernovae in literature. Initially with the 1Cs, and all of them had this oxygen feature. But what was interesting is that as it evolved, it didn't look like a 1C, and it started to look more like some calcium-rich transients, and it started to look like this supernova 2018 GYG. And it also started to develop very weird features, like the calcium feature here was like really big. We didn't really understand what that was, but we started noticing consistency between like these weird transients that I randomly found in literature that were also double detonation candidates that had some of these features. So just to compare quickly 19 EIX with 11 FE. So obviously the light curve doesn't match, and just to show you a quick comparison of the spectrum. At early times, we don't have any of the silicon. It looks different, but especially at maximum light, that is when you see like those huge discrepancy in the colors as well. Okay, what about the color evolution? The color evolution was also interesting because even though the light curves look like a type 1C, the color did not look like a 1C. So this is the color from maximal light in the B band. So here in the black is 19 EIX, and as you can see, the 1Cs are like down here. And you notice that it starts off sort of in the same color, it's like redder, but then as it evolves, it gets a lot redder and it starts to look more like this one. Unfortunately, there aren't many double detonation objects in literature to do a comparison, but the one object that I did find was this peculiar 2016 HNK. So I also ran some of the TARDIS models. So it's a radiative transfer code that calculates the excitations of the plasma, assuming a homologous expansion. And so I started off with the normal type 1C model. And all I did was change a little bit of the abundances. So we noticed that for the 1Cs, they didn't have a lot of oxygen. So I reduced the amount of oxygen. I changed the temperatures to see if perhaps a 1C could explain the models. The 1C models can explain the observations for the 19 EIX. And we were able to get them to see sort of like the 19 EIX, but we had a very difficult time getting rid of the oxygen feature. Like no matter how much we tried, it was very difficult. And so we also did a comparison with these double detonations. So these are models from various people, so Poland, Sim, and Cromer. And one thing that we noticed, I wasn't aware of like the diversity of the double detonations. You can have very dim events to brighter events. And what I noticed was that this model matched the data not perfectly, but it sort of followed the light curve. And I want to point out that these models were not customized for my observations. These are models that I took from literature. I was just trying to do a comparison and see if this is something that could be explained. Yeah.
So, until now we've been talking about double detonation and comparing with the models, but Abby Poland's double detonation models are all sort of either 1D or 2D fairly typically, and you're talking about a scenario where there's helium explosion on the shell, creating a shock wave that goes to the core, that triggers another explosion in the core somewhere, and then the entire thing blows up. So that's sort of a recipe almost to have some amount of asymmetry in the explosion, which you might expect to find in like spec pole signatures or something else. But is there any work on adding in asymmetry as a parameter in the models? What are the signatures one might expect to find with that?
Yeah, no, that's that's really interesting because you're absolutely right. Depending on the viewing angle, you would be able to expect to see different, either more reddening, depending on where the explosion happened. So these are just 1D models, but in the other scenario or the other case that I'm going to show you, I also compare it with the 2D models. But there has been a lot of work done by Ken Chen with these 2D models, and I was able to use those for the latter scenario. But you're absolutely right. I think even when I was looking at a similar explosion of the same mass white dwarf and like different or the same size of the helium shell, depending on the angle, you would expect to see different observables too. So did that answer your question?
I guess you're going to show us the comparison in a little bit. I'm curious to see like what actually changes.
That what mainly changes are the colors. Because depending on the viewing angle, if the explosion happens like at your viewing angle, you'll see a little bit more of like the helium ashes in your point in your viewing angle. And so it just really depends where the explosion converges. You would expect to see more reddening if you're looking at that angle. And for the spectrum. So these are so as you can see, all of these double detonation models at maximum light, for the most part, predict this suppression that happens in the blue light. And not all the models match perfectly, but we did see some of them that were able to sort of explain the spectrum evolution of these 2019 EIX. Yeah.
So, sorry if I missed this, but is the main evidence for the double detonation the spectral shape then? Because your light curve just shows one detonation, as far as I can tell.
Well, so the models are not perfect to the data, but they're able to explain why the reddening happens, why we have these calcium-rich feature, which no other model is able to really show, and that is because when you burn all of this helium, you create a lot of like intermediate mass elements. You create all of this calcium moving at really high velocities, and so if you were to compare that with other models, you would not like a lot of these features. So the calcium, you would not be able to see it. It also explains why there's no oxygen is because it gets buried underneath all the helium burning. It also explains why there's such strong suppression. And so the reason why this is what we believe is the right model is like, well, first of all, we didn't have any of these data customized or on any of these models customized to our data, but it's able to explain the key features that were very alarming to us that we weren't able to understand with any other type of supernova.
Yeah. I think the spectrum are much more discriminating. That's following the point that I.
Yeah, the spectrum, because if you only look at the light curves, it can be confusing because they could look like a 1C.
Right.
But the spectrum, you get more of an understanding of what was burning and what are some of the elements that were created, and that gives you more intuition of like, well, why are we seeing all this calcium? Why is there no oxygen there? And if it's a 1A, why is there no silicon really present there? I mean, there is some, but the main discriminant is the spectrum. Okay, so to recap, double detonations are not perfect. Also, these were like the 1D models, but but they're able to explain really well the features, as I mentioned, why there's no oxygen, why the red colors and the calcium features. But again, they're not able to replicate everything about our object. So I'm gonna go through another scenario with a thin helium shell. So this one was interesting too. Well, it was originally classified as a type 1a. So the brightness is pretty typical of what you'd expect for a normal type 1a. It was like minus 19.3, a little bit brighter. And what was interesting at first from the light curves is that it was a little bit outside of the Phillips relationship. So based on its brightness, it declined a little bit slower than we would expect. But then depending on who you talk to, they can argue that, well, if the error bars follow roughly similar with the error for the Phillips relationship, maybe it can still be a normal 1A. Now the spectrum is a little bit different because starts here like with these really red colors, and it starts to evolve to look something more similar about type 1a supernova. But when I first saw this, that's when it caught my attention, because that's not what you would expect to see. It's especially at these early times, type 1a supernova are expected to be a little bit bluer. So we did a comparison of the spectral evolution with different type 1a supernovae. And for the most part, the one thing that we noticed was that the silicon was not as present. It wasn't as strong. But one thing that we also noticed was that there was a titanium feature. And the titanium features are mostly seen in 91 PG lights, and typically their temperatures are lower, and so that's why you see the titanium. But what's interesting is that this is a brighter supernova, or a brighter type 1a. So that was really interesting. But the color evolution was so interesting because this is 22JOJ, and as you can see, it starts off really red, and then it starts to look like a normal 1a. So normal 1a's are here in the pink. So it starts really red, and then it starts to look more like a type 1a. So then if you didn't have these observations of this early light curve or the spectrum, and you started up here, you would think that perhaps this was a regular 1a because it has similar absolute magnitudes, and also the colors behave pretty similar to a normal type 1a. So that is really important to emphasize, is that these early observations was really critical for these. Okay, so then we also looked at delayed detonation alternatives, maybe if there's more mixing happening where a lot of, so normally you have like a lot of the nickel at the center, but perhaps if you have some mixing and you can get some of the nickel to be more on like the outer layers, perhaps what we were wondering, what would these observations look like? So basically what this transition means is that the larger values of P means larger values means sharper transitions. So what we're interested is in a smoother transition between nickel rich and nickel poor. So meaning that there would be more nickel on the outer layers. But unfortunately, this actually predicted redder color. So that would be P3, so a smoother transition. So that was interesting because that was not what we expected. So then we looked at double detonation alternatives as well. So these are models by Kenshin, and these are models by Poland. And we saw that surprisingly, double detonations can also get pretty bright. So they're at minus 19, minus 19, minus 18. So depending on the thickness of the helium shell and the white dwarf mass. So that was really surprising to see that the range of luminosity for these double detonations. And the spectrum too. What we saw in the spectrum especially for these two models where they were able to predict this early reddening and then the evolution of the supernova to be more like a type 1a. And that is because when you have a thinning of helium shell, you create some of these intermediate mass elements, but not enough to absorb so much of the blue light. Only at the initial phases is where you expect to see this reddening, but because the shell is thin enough, at later phases, it starts to behave like a normal type 1a. So models and theories also predicted that, well, since you're creating some of the helium in your carbon and oxygen white dwarf, perhaps you should be able to see some of the helium in the IR. And so these are some of what the models predicted. So you have, this one here in the blue. So you would expect to see some helium and magnesium. So these are the observations of 22JOJ. We were not able to detect the helium. We don't really know if that is the helium or if that's the helium combined with magnesium. But for the other candidates that were potential double detonations, so these are with the thicker helium shell, they also were not able to find any helium. So we're not sure, so we're really not sure why the helium was not detected in any of the candidates, or whether it's maybe the models were wrong, who knows? Yeah.
So I realize you're not the person doing the actual modeling, but since you brought up this models might be wrong scenario,
Yeah.
what's your take here? Is it that this is fine tuning in some sense, moving the deflagration detonation transition from just the regular delayed detonation models to instead helium shell thickness as the parameter that you can adjust to make whatever kind of supernova you want, really? Or should we really treat these as just two separate explosion scenarios that are still worth considering separately? Like if either of these two models seem to be able to be tuned to explain some of the observations, but not all of the observations, why one over the other?
Like, you mean, why not this model versus?
Yeah, why not just a regular delayed detonation model that gets you at least minus 19.2 at peak?
Well, because the colors didn't match, or the spectrum. Like, you have a lot of, so like the reddening, all the calcium that you see on the spectrum features, like those are not.
But you could tune that also with tweaking the deflagration detonation transition in those models, right? Instead of the helium shell thickness.
I mean, I feel like to create all of that calcium is not something that you can explain physically. You can always fine-tune models, but you need physics or something physical and say, okay, now I understand why the calcium was created because of the helium burning, rather than, yeah, I can always put more calcium, or I can put more whatever, and I can always cheat my way out. But like understanding like how the explosion, but also, like, to your point, these models expected some helium and we didn't see any on the observations. So that's and more theory. So these are the nebular spectrum for these double detonations. And what they expected, actually, it's a lot more calcium than what we've seen. So these two, so 22JOJ is in the black, 2018 AOC, the other candidate that was also a thin helium shell. We also, for none of these candidates, found the helium, or the calcium feature to be that strong. So that's another thing where we're still not sure, and we need, I guess, more data and more models, because also all of these were like 1D models. So perhaps that could influence. So there's still, the double detonation model still has a lot of work to be done in the IR spectrum and also in the nebular models. So these are the list of all the candidates that we have so far in the literature for the thick helium shell and for the thin helium shell. There's more in the thick helium shell, and it's actually not surprising because the thick helium shells are very easy to spot. They're very red. But for the thin helium shell, they kind of blend in with normal type 1a, so they're harder to spot. Okay, so I think we're doing good on time. Okay, so now I'm going to talk about the environment dependence on the brightness of the supernova 1a. So I mentioned that supernova 1a can be standardizable, but studies have found that actually after you standardize the supernova, there's a trend where, so this is the perimagnitude minus the model versus the mass of the galaxy. You see that the larger mass galaxies expect brighter supernova after standardization. That is really interesting, and no one really knows why. However, one thing that I can say about this is that there has been at least some problems on how historically the masses of these galaxies have been estimated. So for the most part, they use optical data alone to estimate some of the masses. And they also assume a parametric star formation history where you have this exponential decay. And so those two methods alone can really bias the masses of these galaxies, because if you're lacking IR data, you're also not looking at, galaxies that are in more dusty environments, or maybe galaxies that have more old stars. And for the parametric star formation history assumption, you're underestimating on perhaps a galaxy that had a recent outburst. And so you're just making assumptions, so that could also be a problem. But a better way to do this would be to collect data in the optical and the IR and do a parametric star formation history, not parametric star formation history that can be more flexible to your star formation histories. And so that is the work that I've been doing at Space Telescope in Johns Hopkins, is that we do have a list of supernova 1a from the Pantheon Plus sample. They have been doing a lot of work on cosmology. Type 1a cosmology is the largest and most precise sample of type 1a supernova. They have about 1,500 supernova likers. They collected all this data with 18 different surveys, and their goal was to infer cosmological parameters. So we're taking advantage of the fact that we know the locations of these type 1a supernova galaxies, the supernova and their galaxies, so we can go out and look for optical and IR data. So as I mentioned, we gather the list and we look for data in catalogs for the Cosmos 2020, the Carnegie Supernova Project, and the Stripe 8082 region. We also created our own sample. We look at HST data and data that was already in SDSS archival, all of this archival data. And so we ended up with a total of 320 galaxies with optical and IR data. So, okay, now our goal is to revisit the mass step and see how, after with these corrections, how does that affect this correlation that we're seeing. So we estimated the galaxy properties using the Bayesian code prospector. So as you can see here, we're adding not just the optical, but all of the data that we have. And what we found is actually that these masses of these galaxies were underestimated. So here on the pink is a Pantheon Plus sample, and the one in the orange is just optical and near-infrared data, and then the one in the blue is using optical near-infrared data and assuming a non-parametric star formation history. So we went back with the new masses, and we saw that there's still a trend. The main difference is that the masses of these galaxies were shifted to higher mass because previously they were underestimated. Another thing that we noticed is that there is a lack of data here, low mass galaxies, and for the most part, low mass galaxies preferentially they prefer supernova 1a with higher stretch. meaning brighter supernova. Okay, so now I put my machine learning hat on and say, okay, what are the trends between these Hubble residual versus the different parameters that I got from the prospector? So what this is telling you here, so this is the Hubble residuals. And the length of it tells you how correlated it is, and the direction tells you how correlated it is in proportion to that parameter. So for example, the Hubble residuals are most correlated with star formation rates, but because they're closer. But if they're exactly the opposite would mean that they're anti-correlated. So if one goes up, the other one goes down. So from this plot, you can see that the Hubble residuals and the dust of the galaxy were vertical, meaning that there isn't much of a correlation. But the Hubble residuals and the metallicity, which is the lux and so, were not exactly the opposite, but there was some anti-correlation. So we went ahead and looked at the metallicity. So we divided our data into 3 different samples. A sample of low metallicity, middle metallicity, and high metallicity. Low metallicity being anything subsolar. So we went ahead and looked at this. And we noticed that if you only look at the low metallicity galaxies and supernova, the relationship is a lot stronger. Before it was 0.04 and now it's about 0.08, which doubled. More interestingly is that when we remove the low metallicity sample from the entire sample of the study, we notice that the trend essentially disappeared. One thing that I will mention that is really important is that because we removed the low metallicity galaxies, it also removed a lot of the low mass galaxies. So it could be that our slope or their fit could be biased because there isn't as much data and there is a data imbalance. But we do think it's worth noting that there is at least a strong correlation with.
So your metallicity is a characteristic metallicity for a whole galaxy based on the Sloan aperture, or what's the measurement that you have
For
for the metallicity? Where do you have that measurement from?
like, how did I estimate it?
Yeah, is it galaxy metallicity?
Yeah,
based on
oh yeah, it's a galaxy metallicity. They were all estimated with the prospector code. So you can give it, it's a sampler where you give it a parameter of masses, you give it like metallicity and ages, and it samples and it does a probability distribution and it outputs the most probable masses and metallicities. But these are all global properties. They're not local by any means. So that's another thing to point out is that all of these are global properties, which could be very different locally. Okay, so we also looked at to see if this could in any way affect the cosmology if we remove the low-C sample from the one that we had originally. And we didn't notice much of a change. The Hubble constant changed very, very slightly, but not enough to make a big difference. So yeah, to conclude things, we revisited the mass step with the addition of near infrared data, far infrared data. We use more flexible models to account for the star formation history of the galaxies. And we did find the correlation that the mass dip could potentially be due to the metallicity. However, there has been a lot of discussions of whether this could be primarily due to either age or metallicity, because low metallicity are also galaxies that are younger. So to disentangle between the two has been, well, I guess we haven't done that, but that's something that we need to look forward to and have more discussions and collect more data. So ideally, if we can fill in this gap and get more data, optical and the near infrared, we can like fill in this gap and see whether these trends still exist. Yeah, and more, we need more low mass galaxies to test this.
This is mostly because these, it's like you assume there's a constant supernova rate per unit time per unit mass. If you have 10 times less massive galaxies at 10 times fewer supernovae given amount of time. Is it this problem just that you have to wait longer to get enough supernovae from those galaxies, or what?
Like why the ages are
No, why are they so close compared to the more massive galaxies?
I think it's because once we applied, well, I think that's a good question. I have to think more about it, but at least for what we're seeing here is that when we re-estimated the masses of the galaxies, they all shifted
True.
to higher mass. So a lot of the ones that they were lower mass galaxies, they shifted to higher.
Like you've got, I'd say you've got maybe a factor of 100 to a factor of 1,000 there in host mass. And so for every 1,000 supernovae in a 10 to the 11 solar mass galaxy, you have 10 in a 10 to the 9 solar mass galaxy. Is that just the problem, or is there some detection efficiency issue that's the problem here?
That's a great question. I actually am not entirely sure why that is.
I mean, with Pantheon Plus, it's very possible it's just a selection effect because we targeted fields where we had an overdensity of galaxies, which also meant that there was an overdensity of bright galaxies,
Yeah.
and big galaxies rather than low surface brightness speedy galaxies. We wanted more supernovae. We didn't particularly care where they were coming from.
And I guess also it's easier to get the data for more massive galaxies because they're brighter. So you're able to get the optical and the near infrared data easier. Whereas like if they're too faint, it's too difficult. Sometimes you think that there's nothing there, in fact. So I think it's like a bias effect on the way that we selected the data.
So similar question, are we still stuck with doing prospector with global host photometry, or can we move to, I don't know, using DESI and DESI2 foremost to get real spectroscopic metallicities in the future?
That is something that I want to do for the future, but there has been some papers that have done more local studies, but the samples have been really small. And they also, for the masses of the galaxies, they also looking at the optical data. So definitely in the future, that would be something that I'd like to propose and perhaps work more on. But for now, there hasn't been much done for the local part. Oh, there's one more question.
Oh, yeah,
Yeah.
I was wondering, could you say more about your Hubble constant measurement? Like it's much, is it lower than what Pantheon published? And you think it's because of this mass measurement difference? I think it's lower, and yeah, do you have any?
Well, from our sample, we didn't compare it directly with the full Pantheon Plus because they had a larger sample. It was 1,500, with ours was 220, so it wouldn't have been a fair comparison. But for the most part, it remained unchanged when we removed the low metallicity.
I may have missed this, but when you ran PCA, what were the main contributors in your parameter space for PC1 and PC2?
Yeah, the main ones where the metallicity was actually negatively correlated. And so that is where we look, because that means that if the Hubble residuals were increased, that means that the metallicity was decreasing. So that is where we saw, but we didn't see anything that was like super positively correlated that pointed in the same direction and that was close to it. It was mostly like the closest one, the star formation rate, and then the metallicity was like more anti-correlated. We also saw age, but it was less correlated. And so that is the reason why we decided to look at the metallicity.
Thank you. Jacob?
I had a question also on the same metallicity thing. I would agree that the optical and infrared photometry might not be that sensitive to the metallicity, especially compared with like the optical spectroscopy. Have you looked at other correlations that would kind of test that? Like, one thing that kind of pops out is that when you remove the low metallicity cases, you still have some low mass galaxies. Like if you plot just mass versus metallicity, what you infer, do you get something that's similar to mass metallicity, or is it offset, or do you get a lot of scatter?
Well, I guess we wanted to see it what's in relation with the Hubble residuals, because that is where we see these discrepancies in brightness. So I guess that would be like this step where this is just a metallicity sample, but we didn't directly do the low metallicity versus mass and see if there's a correlation. But yeah, that would be something to consider and look into.
Other questions for this week? I'm gonna take, can you go back to the Hubble residual contours? So how has it been being at Johns Hopkins University next to Professor Adam Rees and training?
I know. Don't tell him. He would be really upset. 'Cause he's likes the 74 and but anyway, let's move on.
On that note, so let's thank Esther again and congratulations on our